So American black bears. The American black bear is one of 8 bear species in the world. It is the smallest North American bear and the most common bear species on the planet. In 1969, Dr. Michael R. Pelton of the University of Tennessee initiated a long-term study of the population in the Great Smoky Mountains National Park. One aspect of the study was to develop a model that could be used to predict a bear's weight, since it's not practical to weigh bears in the field. One variable thought to be related to the weight is the length of the bear. The following data represent the lengths and weights of 12 American black bears. So we have the length of the bear paired with the weight of the same bear. We have 12 different bears that we've measured both the length and the weight of. So again, the idea here is this Dr. Pelton is doing a study of American black bears. And so one part of that study wants to know how much a bear weighs. However, if you're in the Great Smoky Mountains, you can't very well get a bear to step onto a scale so that you can weigh it. Even if you tranquilize it, for example, you can't really do that. So as part of this study, they want to try to determine if there is a way that they could predict a bear's weight based on the length of the bear. Now, there are probably other variables that would also help in identifying how much a bear is going to weigh, but this is going to be a relatively simple model to predict what a bear would weigh. So, part A, which variable is the explanatory variable based on the goal of the research? So again, in this particular study, the purpose is to try to be able to predict the bear's weight by using the total length. Therefore, that means the length of the bear is going to be the explanatory variable. We're going to use the length to explain why the weight is what it is. So which variable is the explanatory variable based on the goal of the research? The length. Part B, draw a scatter diagram. So since length is going to be the explanatory variable, that's going to be the X variable. And that means the weight is going to be the response variable. So that's going to be the Y variable. So we want to draw a scatter diagram, and I'm going to use StatCrunch to do this. And so I want to create a scatter plot. Well, if you'll remember how to do that, we can go to Graph, and we can go to scatter plot. My X variable is the explanatory variable, so that's total length. My Y variable is the response variable, so that's the weight. And I'm going to say compute. And when I do that, I get this scatter plot. So do you think that there's a linear relationship? Is there a linear relationship between the length of the bear and the weight of the bear? It really kind of is hard to tell with only a few data values. So here we only have 12 points. It would probably be easier to tell if we had more like 50 points or 100 points or something like that. That would probably help. What I will say is if you look at this generally, they are scattered, but there is a relatively upward trend for the most part. So as we're going from left to right, it is going up. And so again, my point is the scatter plot alone isn't really sufficient to be able to tell if there's a linear relationship. Remember, we talked about that we might be able to skew it. So if I were to like just stretch out my window here, so I'm basically changing the scale, that looks more linear now than it did in the first place, right? So I can sometimes make it look more or less linear depending on the scale of my graph. So again, the point is we really need to do more than just find the scatter plot. So part C, and I'm not going to bring back my screen, but part C says to determine the linear correlation coefficient between the weight and the length. So we want to find the correlation coefficient. So if you'll remember in StatCrunch, to calculate the correlation coefficient, I'm going to go to Stat, and I'm going to go to summary stats. And instead of choosing columns, we're going to choose correlation. So if I select correlation, I get this window. I choose the two variables that I'm trying to determine the correlation between. So in this case, the length and the weight. And other than that, all I have to do is say compute. And when I do that, I get the correlation coefficient, which is 0.7039. So I'm going to write that down here. R equals 0.7039. And now I'm going to come back and show you my notes again. We've answered C. We have the correlation coefficient. So part D, does a linear relation exist between the weight of the bear and its length? And particularly, we're talking about American black bears. So is there a linear relationship? So R equals 0.703. That's not extremely close to 1, but it's somewhat close to 1. It's closer to 1 than it is to 0, for example. So that might be an indication that we do, in fact, have a linear relationship. So the way I really tell for sure is by conducting my test. So I'm going to use this table. And again, this table comes from Table 2 in the appendix of the textbook. In this particular case, I have a sample size of 12. So the critical value for correlation coefficients is 0.576. So I have a critical value of 0.576. I take the absolute value of my correlation coefficient, 0.7039. So take the absolute value of 0.7039, which is 0.7039, and that is bigger than 0.576. So because the absolute value of 0.7039 is bigger than 0.576, there is a linear relation. So even though our scatter plot initially wasn't all that convincing that there was a linear relation between the length of the bear and the weight of the bear, our correlation coefficient indicates otherwise. Again, because the absolute value of 0.7039 is 0.7039, and that's bigger than 0.576, that indicates that there is a linear relation. The only last item that we have is just a caution. If data used in a study are observational, so if we're doing an observational study, such as we're doing with the bears, we cannot conclude the two correlated variables have a causal relationship. In other words, sometimes people want to overstep, and they want to say that just because two variables are related to each other, there's a correlation, that means one causes the other. And that is just not necessarily true. It's possible that it's true, but there's no guarantee that it's true. So again, just a word of caution. Just because we have an association or a correlation between two variables, that doesn't necessarily mean that one causes the other. The explanatory variable doesn't necessarily cause the response variable just because they're related. And just as an example of this, a lurking variable, we've talked about those before, is related to both the explanatory variable and the response variable. For example, as air conditioning bills increase, so does the crime rate. And this is true. As air conditioning bills go up, crime rates go up. So does this mean that folks should turn off the air conditioner so that crime rates will decrease? Well, that's absurd, right? Certainly not. In this case, the lurking variable is the temperature, the air temperature. As air temperature rises, both air conditioning bills and crime rates rise. So again, just because air conditioning is correlated to crime rate, that doesn't mean air conditioning bills are causing the crime rates, right? There can possibly be some other variable that is affecting both of the explanatory and the response variable. And that's the idea. So again, don't overstate what you've learned from a correlation. Just because two things are associated, that doesn't necessarily mean that there is a causal relationship.